Hot rolling process. Hot rolling is a metalworking process where steel is plastically deformed at high temperatures. This process reduces the thickness of the steel while improving its mechanical properties. The process is ideal for producing sheets, plates, and strips used in construction, automotive, and industrial applications. The main stages of hot rolling involve reheating, scale removal, roughing, finishing, and coiling, each designed to achieve specific product dimensions and quality. Reheating furnaces. The process begins with reheating slabs in specialized furnaces, typically walking beam furnaces, to around 1,200 degrees Celsius. The purpose of reheating is to make the material malleable and suitable for rolling. Proper heating ensures uniform material properties by dissolving carbides and nitrides. Insufficient heating can result in defects and improper mechanical characteristics. During reheating, the hot steel reacts with oxygen, forming a layer of oxide known as mill scale. This oxide layer must be removed before rolling, as it can lead to defects when pressed into the material's surface, affecting the quality of the final product. Mill scale cleansing. To remove mill scale, high-pressure water jets, 160 bar, are used to spray the steel surface. This process not only cleans the surface but also ensures that no residue remains that could affect the rolling process. Repeated cleansing may be required during intermediate stages to maintain surface quality. Roughing mill. In the roughing mill, the material undergoes significant thickness reduction. Starting from an initial thickness of around 22 centimeters, the material is reduced to about 3 centimeters through multiple passes. The roughing mill consists of a 4-high rolling mill, which includes 2 backup rolls and 2 working rolls. The backup rolls provide stability, while the working rolls make direct contact with the material, ensuring smooth rolling. Vertical rolls are also used to control the width of the material during this stage. Multiple surface cleanings are conducted between passes to remove any newly formed scale. Surface cleaning. To maintain surface integrity, the material undergoes additional cleaning processes during and after roughing. High-pressure sprays are used to ensure any remaining oxide layers are eliminated, providing a clean surface for further processing in the finishing mill. Coil box. After roughing, the material, now referred to as a transfer bar, is rolled into a coil in the coil box. This step serves 2 purposes. It saves space during processing. It ensures temperature equalization by minimizing temperature differences between the ends of the transfer bar. Temperature uniformity is essential for consistent rolling and mechanical properties in subsequent stages. The transfer bar exits the coil box at approximately 150 degrees Celsius and undergoes further scale removal before entering the finishing mill. Finishing mill. The finishing mill is responsible for achieving the final thickness and dimensional accuracy of the material. The material, now called a strip, passes through 6 4-high rolling mill stands, reducing thickness to between 16 mm and 1.8 mm. An uplooper is used to control line speed, tension, and strip profile. Horizontal adjustments in the early stands manage profile accuracy, while later stands focus on flatness. Ensuring proper profile and flatness is critical before post-processing to avoid defects in the final product. Cooling and coiling. Once the desired thickness and flatness are achieved, the material enters the cooling section. The cooling rate is adjusted based on the material's intended properties to optimize microstructure and mechanical characteristics. After cooling, the strip is coiled at temperatures ranging from 150 degrees Celsius to 750 degrees Celsius, depending on the final specifications. Coiled strips can be shipped directly to customers or undergo additional processing, such as cold rolling, annealing, or coating, to meet specific requirements. The production process of high-quality aluminum printing plates. Aluminum printing plates are vital components in the printing industry. Known for their durability, precision, and reliability, the production of these plates involves a complex and carefully controlled process that ensures exceptional quality and performance. Below is a detailed overview of the key steps involved in the production process. The process begins with molten aluminum extracted through electrolysis. The molten metal is poured into large molds to form ingots, which serve as the foundation for further processing. These ingots typically weigh several tons and are crafted for strength and dimensional stability. Once solidified, the ingots are sawed and scalped to remove surface impurities and achieve a uniform size. This step prepares the ingots for subsequent heating and rolling processes. The ingots are then preheated to approximately 500 degrees Celsius to ensure even internal and external temperatures. This step softens the aluminum, making it easier to process during the rolling stages. The preheated ingots are passed through a series of massive rollers in the hot rolling section. The intense pressure and high temperatures reduce their thickness significantly as they are flattened into long sheets. This process involves multiple rolling passes, gradually thinning the aluminum to around 4 millimeters while maintaining uniformity and structural integrity. The sheets are then coiled for easier handling and transportation. The precision of the hot rolling process ensures consistent thickness and material properties, preparing the aluminum for further refinement in the cold rolling stage. After cooling, the coils are sent to cold rolling mills, where the thickness is further reduced to between 0.15 millimeters and 0.3 millimeters. Cold rolling ensures a smooth surface finish and precise thickness required for high-quality printing plates. Shipping coils to coating plants once the required dimensions are achieved. The aluminum coils are transported to specialized coating plants. These facilities are equipped to transform the coils into printing plates. From rolls to printing plate at the coating plant, the aluminum coils are prepared for transformation into printing plates. The process begins with unwinding the coils, which are then fed into a continuous production line. Each stage in this process is carefully controlled to ensure consistent quality. The aluminum is first etched and electrochemically grained to clean and roughen the surface, ensuring proper adhesion of the coating. Afterward, a light or thermal-sensitive coating is applied, which forms the image-receptive layer. The aluminum coils are unwound to feed the continuous production line. The first step in the preparation process is etching, where the aluminum surface is chemically cleaned. This removes any residual impurities and prepares the surface for further treatment. Coating of the aluminum sheets are then coated with a light or thermal-sensitive layer. This coating forms the image-receptive layer of the printing plate, which is responsible for holding the design to be printed. Surface inspection to guarantee flawless quality. Advanced CCD or laser inspection systems are used to scan every square nanometer of the coated surface. This ensures uniformity and detects any imperfections. Visual inspection following automated inspection. The plates undergo manual visual checks to further verify their quality and consistency. The coated sheets are then trimmed and cut to the required sizes. Before packaging, the plates undergo a final round of inspections to confirm their readiness for shipment. The finished plates are carefully packed in light-tight, recyclable boxes and are prepared for transportation to customers worldwide. The portable pipe cutter is a versatile, transportable machine designed for precise thermal cutting of large diameter pipes. It enables on-site cutting, ensuring accurate bevels and complex shapes for welding preparation. Scaffolding provides stable support for operators during pipe cutting operations. The rotator with a speed controller is a crucial component that rotates large diameter pipes smoothly during cutting. It ensures precise alignment and consistent rotation speed, enabling accurate bevel cuts and complex profiles while minimizing errors and enhancing cutting efficiency. A safety overhead crane is designed to lift and transport heavy loads in a controlled, secure manner. It features safety mechanisms, including load limits, emergency stops, and proper rigging to prevent accidents. Initialization point and reference lines ensure accurate alignment and positioning for cutting. Dry run and final check are critical steps in the CNC pipe cutting process, ensuring precision and safety before starting actual cutting operations. Dry run. This is a test run of the CNC cutting machine without any material. During a dry run, the machine simulates the cutting process based on the programmed instructions, allowing operators to verify the machine's movements, speeds, and accuracy. It helps identify any potential issues, such as collisions or misalignments, before actual cutting begins. The dry run also ensures that all the necessary paths, angles, and bevels are correctly set up according to the project specifications, reducing the risk of errors or material wastage during the real operation. Final check. The final check occurs after the dry run and involves a thorough inspection of both the machine setup and the cutting program. The operator reviews all parameters, such as cutting speeds, tool positions, and material sizes, to ensure everything aligns with the provided specifications. It includes verifying safety measures, such as ensuring the machine's emergency stops and safety shields are functional. The final check also involves confirming that the correct tools are installed, the material is securely clamped, and the cutting path is clear of any obstructions. The manufacturing process begins with plate receiving and storage, where raw steel plates are received and stored in a controlled environment to prevent damage. These plates then undergo plate shot blasting LSAW, a process that removes contaminants. Next, an edge milling machine. The pre-bending line, crimping press, is then employed to slightly bend the edges of the plates for forming. The steel plates are then shaped using the pipe-forming JCO press. Tack welding is used to hold the shaped plates in place before the final welding process. The next phase is LSAW inside welding, which involves welding the internal side of the pipe for structural integrity. Once welded, the pipe undergoes mechanical expander treatment to ensure that the pipe maintains its shape and is free of deformations. Non-destructive testing, NDT, is then performed to detect any internal or external defects that could compromise the quality. Following this, hydrostatic testing ensures the pipe can withstand high internal pressures without leakage. The machining and testing of pipe ends ensures precise alignment and surface finish. Dimensional control guarantees the pipe meets specific size requirements. Finally, final inspection and marking ensure the product's quality and compliance with industry standards before shipment. AGPC's modern manufacturing plant delivers high-quality, reliable, and durable LSAW pipes. Dirostahl hammer forging is rooted in a centuries-old tradition, with the forge still being the core business of the company today. While the process has evolved, the fundamental principles remain unchanged. Historically, forging was one of the oldest crafts practiced by mankind, and despite modern advancements, it continues to play a central role in Dirostahl's operations. In modern-day forging, raw materials are heated to temperatures ranging between 1150 and 1250 degrees Celsius. Smaller pieces are then forged using steam hammers, which have impressive weights between 300 to 6,000 kilos. Larger workpieces are manipulated with hydraulic upsetting presses. The company produces a wide range of forged products, ranging from 10 kilograms to 2,500 kilograms per piece. Though today's equipment is far more advanced, the craftsmanship and teamwork involved in the process are still essential. For instance, smaller forgings are still moved by hand, requiring skillful coordination with tongs and levers. This process demands high levels of expertise and precision from the workforce, who ensure that every piece meets the required standards. To maintain quality control, each forged piece is hot-stamped with an order number for traceability and identification. For larger forgings, electro-hydraulic handling equipment is employed to manipulate pieces under steam hammers, weighing up to 6,000 kilos. The open die forging process allows Dirostahl to produce highly customizable forgings in both major orders and serial production. ELLWOOD Aluminum, a division of the ELLWOOD Group, operates a state-of-the-art aluminum casting facility in Hubbard, Ohio, specializing in the production of large-diameter aluminum ingots, billets, rectangular slabs, and cast plates for customers worldwide. A key feature of their operation is the integration of their holding furnace with the Wagstaff casting system, allowing precise control over the tilting of the furnace directly from the control room. ELLWOOD Aluminum utilizes vertical direct chill (VDC) casting technology, a process that involves pouring molten aluminum into a vertically oriented, water-cooled mold. This method ensures rapid solidification, resulting in a fine-grained, high-quality aluminum product with reduced internal stresses and improved mechanical properties. The facility is equipped with dedicated melting and holding furnaces, a casting pit capable of producing lengths up to 360 inches, and two 40-ton cranes for material handling. This setup enables the production of some of the largest aluminum ingots and billets in North America, catering to industries such as aerospace, automotive, defense, and transportation. The manufacturing process begins with melting prime and scrap aluminum in a 60-ton reverberatory furnace. Samples are analyzed by on-site metallurgists to ensure they meet exact customer specifications. Alloys are then added as needed, and the molten aluminum is transferred to the holding furnace. The integration with the Wagstaff casting system allows for precise control during casting, utilizing VDC technology to produce high-quality ingots and billets. Post-casting, the products undergo thermal treatment to homogenize the chemistry throughout the entire ingot, followed by machining to meet specified tolerances. Finally, the products are carefully packaged to ensure they remain intact during shipment to customers. The manufacturing of heavy industrial cranes involves advanced engineering, strict quality control, and precision assembly to produce high-performance lifting equipment. Companies like Seven Crane, a leading Chinese manufacturer, specialize in designing and producing a wide range of cranes and lifting solutions. Their product line includes overhead cranes, gantry cranes, jib cranes, electric hoists, electric winches, and various crane accessories, such as hooks, buckets, and crabs. The production process begins with detailed design and engineering, incorporating European standards and modern technologies to ensure durability, reliability, and safety. High-quality raw materials are used to fabricate structural components, which are then processed through cutting, welding, and machining operations. Advanced techniques ensure that parts are produced with precision, to meet strict performance requirements. Once the components are manufactured, they undergo rigorous quality inspections to ensure compliance with international standards, including CE certification for export. Testing involves load capacity verification, operational performance checks, and safety assessments to guarantee reliability under heavy workloads.